Uh, Hi Ronit, am I audible to you? Okay, so yeah, it's already 6:04. So we can start. Slowly. Others will join. Okay. Okay. As I mentioned, I guess, Ronit, this is your first session, I guess. If you are okay, you can just introduce yourself. Like, where are you from? What you're studying? And did you attended a gate before? Huh? If there is any mic problem, you can type there, and right after that, we can proceed with today's topic. Today's topic is, as I mentioned in the website as well as mentioned in the previous class. Today topic is the dimensionless number and as well as similitude. So we will start with the similarities or similitude. What is exactly the similitude, and why do we need to do, and what are the necessary conditions for model and prototype studies and all. And later, and right after that, we will talk about the basic dimensions, like we use. So here in this today's lecture, I am going to deal with SI units only, not FPS and other units. So the SI is a standard unit, so we will use SI units only. Muralidharan, kindly mute yourself. Yeah. We will right after that. I'll show how we can calculate the dimensions, like in MLT format, and after that we will see the some important dimensionless numbers and their applications in solving problems. So this is the outline of the presentation. Okay, let's get started. Sorry, this is session 4. Okay. Welcome to session 4. Today, myself, Kannaganti Bhargav Kumar, I'm a PhD scholar in IISc in Institute of Science, Bangalore. Yeah, as I'm mentioning in every class, this session also I'll mention. So I have attended GATE 2 times before joining into the PhD. One was in 2015. 2015. And after I and the second attempt was GATE 2018. So in both the attempts, I've done the self preparation only by referring some few books. So yeah, so like the self motivation is a main driving mechanism for a success. So I hope these sessions will be motivated you, and give the perception about the gate and other things. So see, for a new joinees, this session will keep it more like an interactive session rather than the lecture and the student session. See, because I am also student, so you can freely ask whatever the doubt you have. Even the doubt may be mine, very small or trivial. You may appear as a trivial, but still you can open up yourself and ask. I'll help you out. So let's get started. So yeah, as I mentioned, welcome to session 4. So today we will talk about a similitude. Similitude or similarity, we can also call as similarity, is a theory and art of predicting prototype performance from a model observation. See, so I hope all of you know what is the difference between the model and the prototype. Suppose if there is a before like let's say this is a spillway and this is another spillway. Okay, so this we intended to construct in a field. Oh, sorry, I shared this. Sorry, my bad. Can you see my screen now? Anybody can respond. Like, are you able to see my screen here? Okay, sorry, I'll get started again. Okay, so yeah, welcome to session 4. So let's start. So we'll first see what is the similitude and other things. Yeah. So similitude, and we also called as a similarity, can also be called as a similarity. So what is the definition of similitude? It is a theory and art of predicting prototype performance. See, let's say like these are the two. One is this is a model. This is a prototype. Let's say field. See, this is a size we intended to construct in the dam. But suppose, like, let's say if we construct this one, and if they and our design, if this particular structure does not able to meet our discharge requirements or velocity requirements, then we will lose lot of money. We will lose lot of money. So that's why for any bigger constructions or new designs, designing of new structures, what we our traditionally do is that we will construct a model of maybe a smaller size slash larger size, depends upon the field application. Suppose sometimes we may need to construct a model which has a bigger size than the prototype, like let's say machine part. Some like suppose let's say some part may be very smaller, but when we wanted to perform some experiments, we won't able to see the actual phenomena what is happening. So in that case, we may need to construct a model of bigger size. It's not always that model has a smaller size, it can be a big, large size also. Okay, suppose I given one example here. Suppose let's say when a new aeroplane is designed. So what we do, like let's say we designed aeroplane, but it has to be sustained, and it should be very safe against landing, and it should be very safe against the taking off, as well as it should able to withstand a low pressure and as well as a high pressure. All these things has to be tested and a general scale model. And as well as we also need to test some smaller parts as well, like a propellers and the AC conditions or oxygen. All these things will be tested before it releasing into the market. Suppose let's say all of you know that aeroplane building up of aeroplane or designing of aeroplane is very costly phenomena. So suppose let's say if we design this aeroplane, but if that aeroplane is unable to go beyond the 1 kilometer, 2 kilometer, then all the money is lost. So now what we used to do traditionally, we will build another aeroplane of a model, and we will create a environment which we would like to we will like to create an environment which is uh, similar of practical environment, and we will test those things, like say for example wind tunnel. So all this like aeroplane and turbines, they all these things will be tested in the wind tunnel. Sometimes we may need to test in the water also, like with by adding so wind tunnels, I think many of you know wind tunnels are like water tunnels. So we will test all these prototypes in the either one of these by considering the effect of density and other things. So this is economical, considering effect of density and other physical properties. So this is a economical way to economical way to test as well as a design, because designing it's not a one time process, like it will be a repetitive process. Sometimes if our prototype does not met the criteria, then again we need to redesign, or this kind of a to and fro process will happen. So to avoid this thing, what we do is that we will create a model, and we will do all the experiments on the model, and we will, once the model provide a satisfactory results, then we will give the production section to build the prototype. So this is the traditional way to do. Okay. So like to build some model which should be a replica of prototype, it should meet the model should meet these three similarities. First one is geometric similarity, second one is a kinematic similarity, third one is a dynamic similarity. So if the model is able to provide a similarities in these three criteria, then that is called as a perfect model of prototype. And whatever the test we perform on this particular model will be valid in the prototype. I hope you're clear about this point. Okay, let's read what is a geometric similarity. So geometric similarity refers to the linear dimension. So yeah, the model must be of a same shape as a prototype, but may be scaled by some constant scale parameter. As I have shown, let's say if we have built a spillway like this, but our intended spillway of this size. Okay, this may be model, this may be prototype. Okay, so first criteria, what is that? It should be of a same size, but may be scaled by some parameter. Let's say LR. This is maybe we can denote it with LR. Okay, and the next one, the velocity, that is all about geometric similarity. Let's say what is the kinematic similarity? Let's say velocity at any point in the model flow must be proportional to the velocity at the corresponding point in the prototype of flow. So by a constant scale parameter, let's say if my design velocity at this point, maybe let's say 3 meter per second, for example, then the model also the velocity should be maintained by some, let's say, some Vm with some VR ratio. Okay. So let's say it is V in the prototype maybe 3 meter per second. Vm should be V VR of Em. This is called a scale ratio, scale of velocity ratio. So these ratios, okay. So to suppose if any model is set that is a kinematically similar, and it must be geometrically similar also. That is a prerequisite. And the next one is dynamic similarity. When all the forces in the model scale by a constant parameter to the corresponding. Let's say in the model, like like prototype, we have pressure P at in prototype. In a model also, we should have pressure with some ratio of PP. Okay, sorry. Okay, so yeah, so the kinematic similarity is necessary, but not insufficient condition for the see. Suppose let's say we say that model and prototype is kinematically similar. It is necessary, but it does not guarantee that the model and prototype is dynamically similar. So a model, suppose it is a good, is like a perfect model, then all the three similarity conditions must exist for a complete similarity to be ensured. Okay, suppose that when we build a model, it should meet all these similarities, then it will be like a perfect example for the prototype. Okay, and as well as in another way, what we can say is that all the significant dimensionless parameters must be equal for the model and prototype. Okay, so if we need to build a model in a such a way that all the three similarities must exist, and as well as some of the famous dimensionless parameter must be same, so that we can see in the next slides what is our dimensionless parameters and other all. Before proceeding further, let me introduce a few basics here. Okay, let's say mass. So what are the units of mass? Anybody can say what is the units of mass? Let's say maybe kg. And how we denote with this thing? Let's say symbol m. Okay. So what is the velocity? Suppose let's say length. What is the units of length? Meters. And the symbol is L, capital L. What is the let's say next velocity? What is the units? Meter per second. And how we can write? So it is a meter per second, or nothing but length by time. Okay. So before this, I'll introduce this thing. So how we what is the units of time? Seconds. And what is the symbols to represent small t? So here from this, how we can write L by small t. So L by t inverse. Okay, we can represent in this way. So next one is what are the basic? These are the basic units or basic units. Let's say how we can write acceleration due to gravity in MLT format. So what is acceleration due to gravity? Velocity upon time. So already we know what is the velocity? Length per time divided by time. So how we can represent what is the symbol for length? So L and t divided by t. It will be L by t whole square. Sometimes it can be represented with a capital T also, t square. Then it will be L power minus t square. Okay, this is a way we can. So these are the very necessary. These are the necessary basics for solving the problem. Kindly note down. So let's say we direct like surface tension force. What is surface tension force? So it is like force per unit length. So these are the basics from class 6, class 7. So what is the force? Force per unit length. So how we can write force per length? So how we can write force? Mass into acceleration divided by length. Okay. So what is the symbol for mass? Let's say capital M, and acceleration mlt power minus 2 divided by L. Already what is the symbol for length? L, as I have shown you as before. So this is what is the final format? mt power minus 2. Okay. So similarly, can anybody say dynamic viscosity units in MLT format? Mu. Yeah. So then, like any guess, like how we can write dynamic viscosity in MLT format? It may be a wrong, but you just guess it, like how we can write. Okay. So what is the units of this thing? Dynamic viscosity units are kg per meter second. So what is the kg? How we can represent the kg? Symbol m. And meters of what is the symbol? L. So it will be like L inverse, and seconds T inverse. So this is the units. So it will be like M L inverse T inverse. See, this may appear as a trivial, but these are very necessary while like not only here, even in the not only here, even in the open channel flow and other topics also. So how? So what else we can solve? Let's say, yeah, density. So how we can write density? Density is mass per volume, nothing but kg per meter cube. So it will be like m by L cube. So m into L cube inverse. Okay. These are the few basics to remember. Let's proceed with dimensionless number. So the very first important dimensionless number is the Reynolds number. Okay. So I all of you know why it is very important, because we see that if the like if Reynolds number 5 to 500, Reynolds number greater than 200 2000, you might have seen this kind of values. So this RE classify the nature of flow inside the pipes, nature of flow in pipes. Suppose let's say if the Reynolds number of the flow is less than 500, we say it is a laminar flow, and if it is more than 2000, we say turbulent flow. So this Reynolds number will be significant in pipes, study of pipe studies. Like let's say if you want to construct a the oil carrying pipe, like let's say for example, if you see, I think you all of him know this Dubai, Oman and Dubai pipeline, oil pipelines, and as well as gas pipelines. So it has run for like a 700 kilometers of and 3 meters 3 meters of diameter. So for this kind of designing of these big pipes, we need to construct a smaller model to test the circumferential pressure and tension. All those tests has to be performed. In those cases, the dominant number will be Reynolds number. It means that between the model and prototype, Reynolds number should be same, like a pipe studies. So what is a ratio? What is the formula? Reynolds number is equal to rho into u into d upon mu. So what is the rho here? Rho is the density of flow. So it will be like kg per meter cube, and u is the velocity velocity of flow. It will be like meter per second, and d is the length or hydraulic diameter. We can say simply as a length, and units are meter, and mu is the dynamic viscosity. It is kg per meter second. So if somebody calculates the units of this RE, it will be like a zero only. Let's do that. So kg per meter cube into meter per second into meter divided by kg per meter second. So kg get cancelled, meter, another meter will get cancelled, second will be cancelled. So if you see, this is dimensionless number. So this can be used in any model studies. So the ratio, this is how we can read Reynolds number is the ratio of inertia force to the viscous force. So it is considering the effect of viscous force. That's why it is dominant in pipe studies. Okay. So next important one is a Froude number. Froude number. What is a Froude number? Froude number is the number. Sorry, Froude number is a ratio of inertia force to the gravitational force. So this will be useful in open surface studies. So let's say open channel flow, spillway design, or channel designs. So spillway design is a very important example. So every year you can expect, like every other year or every year you can expect one question from the spillway design. Not design of spillway, like with respect to similitude. Okay, open channel designs. Okay. So if you calculate the dimensions also, it will be like a meter per second, and it is also meter per second square into meter. So square root of it will be like meter per second only. So meter per second will be get cancelled. Even if you see, this is also dimensionless number. Okay. So this is a Euler's number. So it will be useful to study the pressure forces, effect of pressure forces. Okay. So it is nothing but a ratio of pressure force to the inertial force. Okay. Inertial force. So next is a Weber number. Weber number is ratio of inertia force to the surface tension force. Okay. So what this one is the surface tension. So we already seen mt power minus 2, and if you calculate this also will become mt minus 2. So both will get cancelled. So again it will be like a dimensionless number. So this will be useful for the like in the studies where surface tension force is a dominant. Surface tension force is the dominant. So, but in suppose in a civil engineering field, like we mostly dealing with the Reynolds number as well as the Froude number. But a mechanical engineer they'll deal with the Weber number and Euler number. The Mach number is important for the aeroplane designs. Okay, this is very important in the aeroplane designs. So this Mach number is nothing but this MC Mn. It will be like U by C, velocity, local velocity to the velocity of the sound. If the Mach number is greater than 3, there is a relation. Somebody can see this. Then okay. So these are the important dimensionless numbers. But in our case, we are more interested for this about this Reynolds number as well as the Froude number. So most of the time we use these two only uh, to solve the questions. Okay. So let's proceed with the question. This I have taken from GATE 2018 CE set 1. Okay, the question number is 20. So let's read what is the question. A 1 in 50 model of spillway is to be tested in the laboratory. Okay, I already told you before constructing any constructing in the field, we tend to build a model of a similar nature and do all the performance tests. Okay, so a 1 is to 50 model of spillway is to be tested in the laboratory. The discharge in the prototype. So read prototype P of a spillway is 100 meter cube per second. So this is our design discharge. This is our design discharge. The corresponding discharge in meter cube per second up to 2 decimals. See, when there is a fill in the blanks question, you always need to be careful up to what decimals they were asked, whether 2, 1 or 3 decimals. To be maintained in the model, comma, neglecting the variation in acceleration due to gravity. It means that acceleration due to gravity in model equal to acceleration due to gravity in the prototype. Okay. So I just give 1 minute. So anybody can just guess how we can solve this question. So our interest is to estimate discharge in model by, so what they have given, Lm by Lp, which is nothing but 1 by 50. So how we can solve, any idea? What else they have given? Qp equal to 1000 meter cube per second. So this is a 2 marks question. It's a very simple and straightforward 2 marks question. Very easy to score. Anybody can say guess how we can solve this question. And okay, before solving, can you tell me which number is which number we should focus on? So I told spillway construction before also, while explaining that number also, spillway it is used for spillways. So spillway has an open surface. So it means that Froude's number. Froude's number. What does it mean? So Froude's number in model must be equal to Froude's number in the prototype. Then if it is condition is satisfied, then model is good. Okay. So let's see what is the Froude number. How we can write? Velocity divided by acceleration due to gravity into the d. Okay. This is for model. This is for again prototype, like due to d for prototype. So d here, d can be L, means length of a spillway. So see, in Proud's number, d is nothing but a hydraulic parameter. So we can consider this as L. So it can be replaced as V upon root over G into L of model equal to V upon root over G of L upon P. Okay. So let's separate these terms. So Vm divided by root Gm into root of Lm equal to Vp divided by root over Gp into root over Lp. See, in the question it is given that Gm and Gp are same. If you apply square root both the sides, it will be also same. So let's cancel these two. So what we got? Vm by Vp equal to square root of Lm by Lp. So this is a condition we got. This is a relation we got from the Froude's number. Suppose if we want to make this Froude's number should be same in model and prototype, this condition has to be satisfied. So it means that velocity in the model should be of ratio square root of ratio of Vp. So it's nothing but Vm equal to, let's say Lr, we represent Lr, then Vp. So let's say Lr equal to square root of Lr, let's say Vm by Vp, let's say, sorry, Lm by Lp, let's say. Okay. So now what is our interest? Our interest is to estimate Qm. So what is the Q formula? Q equal to A into V. Okay. Let's say if I wanted to discuss right in terms of M, then Q equal to AM into VM. If I want to write QP, then AP into VP. Like AP means area of prototype, VP into velocity in prototype. Let's say if I write Q by QM by QP, it will be like AM by AP, so VM by VP. Okay. So what is the units of area? So maybe area have units of meter square. Okay. And velocity will have a units of meter per second. So what is the symbols for these things? So it will be like L square. So L square of model divided by LP square into VM upon VP. So how we can write this one? LM by LP whole square into Vm by Vp. But we already know the relation for Vm by Vp from the Froude's number. It will be like Lm by Lp whole square into square root of Lm by Lp. So it will be like Lm by Lp whole square plus 1 by 2. All of you know that square root can be written as 1 by 2. So it will be like Lm by Lp equal to 2.5. Okay. So Qm by Qp equal to Lm by Lp whole power 2.5. So Qm equal to Lm by Lp divided by power of 2.5 into Qp. So what is a Qp? Qp is 1000 as given. What is Lm by Lp? Given 1 by 50. So 1 by 50 of 2.5 into 1000. So if anybody can calculate and give me the answer, it will be like a 0.056 meter cube per second. Okay. So it can write in this way. So okay, let's see the solution. So I have already mentioned this is a GATE 2018 CE set 1 question 22. So in this question they have given a 1 is to 50 model spillway is to be tested in the laboratory. The discharge in the prototype spillway is 1000 meter cube per second. The corresponding discharge in meter cube per second up to 2 decimal places to be maintained in the model, neglecting variation in the acceleration due to gravity. So we need, our aim is to estimate Qm. Okay, and given Qp equal to 1000 and Lm by Lp equal to 1 by 50. So while creating a model for spillway, we should ensure that a Froude number in the model should be equal to Froude number in the prototype, because this is a open surface thing and where the gravitational forces are dominant. Suppose if rather than spillway, if we say if it is a pipe, oil pipe or any oil pipe or gas pipe, then we may need to use the either Euler number or Reynolds number, depends upon the fluid is flowing. Okay, so the necessary condition is Froude number in the model should be equal to Froude number in the prototype. And additionally, in the question it is given neglecting the variation in acceleration due to gravity. It means that Gm equal to Gp. Okay, whether square root of Gm or anything, it is will be the same. Okay, so if you see FRM equal to FR Froude number in the model should be equal to Froude number in the prototype. So we substitute the direct formula V upon root over G into L for model as well as prototype. So we can shuffle the terms. So VM can be VM, it should be here. VP can bring it here. and g square root of gl of m can be shifted to here. So in this way we'll shuffle the terms, and g can be cancelled out. So this will be the final equation. So either we can write Vm by Vp equal to square root of Lm by Lp, or Vm by Vp whole square equal to Lm by Lp. Either both the equations are same. So we may write as Vm by Vp equal to square root of Lm by Lp. Okay, this is a necessary condition to be maintained in the model. Okay, so our interest is to estimate discharge. So let's put this discharge, like calculate the discharge in the model with respect to the prototype. So that we know that discharge equal to area into velocity. So we're not interested to calculate whether b into l or anything. Just we'll take the units only, symbol with respect to the symbols. So it will be like lm square, or it can be written as lm by lp whole square. So otherwise we can write it here. I'll write lm square. It can be lm lp whole square. So we can write it in this way, and that finally we'll get 1 by 52 square, 1 by 51 by 2. So it can be like calculated as 2 plus 1 by 2. So if you take somebody LCM, 4 plus 1, 5, 5 by 2. Okay, that is a 2.5. So QM equal to QP into 1 by 50 into 2.5. It will be like 0.5, 0.056, or if you want, somebody wants to round up, it can put it as a 0.06 meter per second. Okay, this is a very important and a straightforward question. So if any question is coming from this dimension also, you can expect the spillway design only. Okay, so let's solve some simple question. I'll wait for this question. Let's solve this simple question. This I have taken from gate 2013 CA. So for this question, I am expecting some voluntary response. Okay. So the group 1 contains the dimensionless parameter, and group 2 contains the ratios. So now we need to match these ratios. So group 1 is a Mach number. So group number contains the dimensional numbers like a Mach number, Reynolds number, Weber number, and Froude number. And the group 2 contain definitions. Let's say ratio of inertial force to the gravitational force, ratio of fluid velocity to the velocity of the sound, like that. Okay. So I'll give to 20 seconds. So just say this answer. Anybody? Answer C. Good. Any other? Just one. You can just guess. Maybe it can be wrong also, but you can just guess. So Muralidharan has mentioned it is a C. Let's see how he has arrived to the C option. Okay. So let's say first Mach number. So we have seen the symbol of Mach number. What is this definition? Velocity of the fluid divided by the velocity of the sound. So where it is there? So it will be like, sorry, 2. So P will correspond to 2. So Reynolds number we should represent with Re. So what is the definition? Inertia force to rho v d upon mu. Inertia force to the viscous force. So where is the viscous force? So it will be like a 3 only. So what is the Weber number? Weber number comes when a surface tension force is dominant. So you should remember surface tension, if is there, then it's a Weber number only. So it will be like 4. Then what is left out? 1 only. So what are the options? Okay, P2, Q3, R4, S1. Correct. Muradharan, you are correct. Option C is the correct answer. Okay. So all of you understood. I'm unable to hear you. Like, can you speak up a little loud? Yeah. You can mention what is your doubt. Okay. Let's move to another kind of important question, as well as like this question is a 2 marks question. So I'm expecting you to work, and see, when there is a 2 marks question, so you can believe that you need to do some steps. It is not main. It is not always you can get a direct answers. You may need to do some kind of a manipulation of the same equations to get this answer. Okay, let's read this question. 2 marks question always requires some effort. We should prepare for that. Okay, so in a laboratory, a flow experiment is performed over a hydraulic structure. Okay, see, hydraulic structure means open surface. Okay, so we can what then which dimension number is a dominant Froude number. Okay, the measured values of discharge and velocities are 0.05 meter per second and 0.25 meter per second respectively. So these values are corresponding to the laboratory. So it has mentioned clearly mentioned. So you observe if the full scale structure 30 times bigger is subjected to a discharge of 270 meter cube per second, then the time scale model to full scale. It means that Tm divided by Tp. So here you always carefully remember it is asked for model to full scale, not Tp by Tm. So we may in a hurry that we may put Tp by Tm, that is wrong. So you should always carefully see that value up to 2 decimals in place. Okay. So from the previous example, we have seen when the Froude number in model and Froude number in the prototype is equal. So what is the condition we got? Vm by Vp is equal to Lm by square root of Lm by Lp. Okay. This is a condition we have seen already. Okay. And as well as from the when we are equal when we do the ratio of this thing Qm by Qp, what we got? Lm whole square by Lp whole square into Vm by Vp in the previous example. I'll just going back, see here from this steps from this. Okay, I'm just writing the same. Okay, so but here velocity we are, sorry Vp. So here we are more interested about t time. So what we can write Qm by Qp equal to Lm square divided by Lp square into. So what is the velocity? How we can write velocity is length upon time, na, L by T. So it will be like Lm by Tm divided by Lp by Tp. So all of you know AB by B equal to C by D. How it will become? AD divided by BC. Okay, I hope you know all these things. So it will be like Lm by Lp whole square into Lm into Tp divided by Lp into Tm from this equation. Okay, so it can be written as again Qm by Qp equal to Lm by Lp whole square into Lm by Lp Tp by Tm. Okay. Why we converted Vm by Vp? Because we don't know what is the velocity in the prototype. So we need to write in such a way that wherever we know the values. So in the question it is given Lm by Lp equal to 1 by 30. Okay, that is our given data. So here they have given. Okay. So now what we do is that we will our interest is to calculate Tm by Tp. Let's say we'll write in this way. Qm by Qp or Lm by Lp whole cube. Or if you directly want to calculate, somebody want to calculate Tm by Tp also, it can be written as Lm by Lp whole cube to Qp by Qm. Anyway is fine, but don't get confused. Don't get confused with any of these derivations. Okay, final step what we do, Tm by Tp equal to what is Lm by Lp? 1 by 30 whole cube. What is a Qp? 270 meter cube per second divided by what is a Qm? 0.5 meter cube per second. So you can get answer as 1 by 5. Nothing but 0.2. How many of you got answer? So let's see the solution. So in the hydraulic structures, we should need to maintain the kinematic similarity to be maintained. Similarity in the velocity in the model and as well as prototype should be same. Okay. So in 2 marks question, you should perform some kind of a manipulation or some kind of effort. You should require some effort because they they'll design 2 marks question in such a way that you need to spend some time as well as you need to put some thoughts in it. So here they have asked time scale. It's not like any velocity other thing. So it is like a time ratio Tm by Tp. This is a typical structure of 2 marks question. So as well as so you need to carefully write and solve this question. So Froude number in model equal to Froude number in the prototype. So these are the equations we derived in the previous question as well. So again, like Qm by Qp equal to Am by Ap into Vm by Vp. This we know. So here what I did is I have written V in terms of L by T. Okay. So this is the final step we got. So this is a continuation. So here this is a way we got. Okay. Qm by Qp equal to Lm by Lp whole cube into Tp by Tm. Okay. So now what I did is I just simply transferred this form to like 0.05 by 2 into 30 divided by 1 whole cube equal to 5. So but so our interest is to calculate Tm by Tp, not Tp by Tm. So this is of Tp by Tm. So careful, this is a Tp by Tm is like 0.2. Okay. So how many of you have understood this thing points? I'll stop here. Mm, like I'll just wait. If anybody have questions, you can just ask me here, or a message, or post it in the message section. I can answer. Okay. So in the next session, what we do is that again, like we'll go back to the hydrology session. So if you see the recent papers, recent gate papers, so they are not focusing on a unit hydrographs or any other things. They are focusing on a groundwater flow. Okay. Uh, okay, they're focusing on this groundwater flow and other points. So what we do is that groundwater flow as well as the aerial rain precipitation as well. So in the next session, we may. So I'll post the schedule. I'll post the content in the website. Okay. So you please check the website for the next session content. So most probably it will be a groundwater flow. So we will see cone of depression and other content. So it will be really interesting, and I'll show how this cone of depression will form, and as well as some few formulas we will use to calculate this discharge. As well as before proceeding into the 2 marks question, we need to see what is the specific retention, porosity, specific yield, all these terms we need to see. Those are the important basics required. Okay. So maybe so now whoever has attended, so brush up your this basics so that it will be easy to relate while I am talking here. So you need to see what is the specific retention, specific yield, porosity, relation between the specific yield, porosity, and other things, as well as like if all of you, if you many of you have seen the paper, like I hope you have seen the paper. So there's one special question always you can observe. Suppose if you put any ink or any tracer inside the groundwater flow, inside the groundwater table. So let's say if you want to see this groundwater, the same tracer at a 100 kilometers or 200 kilometer downstream of the session, downstream of the channel or somewhere. So how much time it will take to reach to this particular location? These type of question is very common in the gate as well as any competitive exam. So we will solve that kind of also. So okay. So great practice test for civil engineering will be uploaded in this. Okay, so okay, fine. Anyway, I'll solve this question so that you can attend this great practice test. So even I'll refer and I'll see what is the test purpose there. And if the necessary, I'll add some more content in the session. So, but in the next session, we will deal with the groundwater flow only. It is kind of a uh, union of geotechnical engineering also. And we may borrow some topics from the geotechnical engineering as well, like a kind of a velocity velocity in pores. So if you see velocity in the pipes or velocity in the channel, which may be different from the velocity inside the ground, it will be divided with some factor of n or something. So all these things will be discussed. So before attending the next session, maybe you can brush up those things so it will be easy for you to understand. So the next session also we may typically do the same. So I'll spend some 20 minutes on the initial concept, and later we will solve 3 or 4 questions and on the same concept, which on the same concept. So it will be easy for you. Okay. So you have any doubts? You can ask me here. Muralidharan or Likita or At- At- yes, Muralidharan. Good evening. Do you have any doubts? I don't know. Maybe I'll talk with the Raghav or any other coordinator, national coordinator, and I'll update in the next session. As of now, so I'm only dealing with the civil engineering water resources session. So I have no idea about other sessions. Yeah, I know all these sessions will be uploaded in the YouTube and it will be communicated to you later also. Huh? I need to do some editing and I'll up. Uh, okay. Yes, yes. They will contact us for a question. So once this has not communicated yet, so once they have contacted, like once they contact us, then the mock paper will be prepared and later will be given to you. Yes, yes. I'll convey this point to Raghava Ramakrishna sir, Professor Ramakrishna. Yeah, yeah. Thank you. So any other doubts you have, Gurvinder or Ronit or Atisha? Atisha. So if you don't have any you don't have any doubts, you can leave the meeting now. It's already 6:57. Thank you, thank you, thank you for attending.